Okay, we're going to finish up by talking about some practical applications of red-black trees, and in particular B trees, which are a general version. So the idea behind B trees is that often the data that we're trying to store is really huge. There's a large amount of data, and we're going to look at a more general model for external storage, where we work with contiguous blocks of data that are big, maybe 4K or bigger, or maybe even a whole file. And all we want to count is the first time we access a page, because the main cost is trying to find where the page is. Once it's read in, we get to read all the page for free, pretty much. So the real property of external storage, that not your local memory, is that the time required to get to a page is way larger than the time to access data within a page. So what we want to do is try to access data that's out externally using a minimum number of probes. That's a model of a file system that is pretty workable. And so B trees are a generalization of balanced trees that allow for this. The idea is to allow not just 2 or 3 keys per node, but a large number, like the number that can fit in a page. So might be m equals 1,000, or m equals 4,000. And well, we've got to have at least 2 keys at the root. And the only other restriction is that we don't want the nodes to get too empty. So we can have less than m, but we want to have at least m over 2. And as you'll see, this is a generalization of 2-3 trees that allows us to build balanced trees that are very, very shallow. Typically, these are set up so that all the data is in the external nodes. And so the external nodes have no links, they just have keys. And they're kept in sorted order. So for example, this is this is m equals 6, this is an external 5 node. So it's got 5 keys, it's got room for one more temporary one. And then what'll happen is when you insert into a full node, it'll split in the same as before, and then we'll pass the split up, causing a split up higher. So the red keys in the internal nodes are copies of keys down below that direct the search. And that's a little extra detail that just makes the implementation a little bit easier, and that's the way that it's usually done. But for now, the main idea is that it's like a 2-3 tree, except that we allow way more keys per node. And then when a node gets filled, it splits into 2, so a node's always between half full and full. So m is 1,000, it splits in 2, then each side has 500. And then we can use that property of the trees in the analysis to show that it's not going to be very many probes to get to any key. So the search is just the same as we've been doing, just generalized. There's a list of keys at every internal node, and that key tells you that then links for every key that give you a place where your key would have to be. This link is for all the keys in the B tree that are between this key and the next one. And in every case it's that way. So if we're looking for E in this B tree, we'd go down the left link, and then it would go down the second link because E is between D and H, and that's just the way it organized. And then when you get to an external node, you just look for it. That's all searches terminate at an external node, and otherwise it's just a generalization of what we just did. And insertion works the same way. We get to the bottom and then we split. So let's look at just inserting A into this B tree. It comes into the node on the left, and then that makes that temporarily over full. It's got one too many, so we split it into 2 nodes, and that causes us to add a new entry into this internal node. In this case, it's a C, which is the smallest one in this new page, and that has to be added. And we can move all those over. There's plenty of time by the memory model. We're only counting the number of times we access the pages, and we get to move things around for free. And you could have some hybrid structure where you use something different for the internal model, but usually it's fine just to do that. Now that one becomes over full, so it has to split, and we have to create a new root, just in the same way as we've been doing. So without seeing all the details, you can understand that the same basic idea is going to work in this this situation where we're dealing with much more memory. And so the end result is that a search or an insertion in a B tree of order m, that's where we're putting m keys per page, requires between log base m minus 1 m and log base m over 2 n probes. And that's going to be a really small number. So say m is 1,000, log base m over 2 is this log base 500. So what power do you have to raise 500 to get bigger than n? In practice, that's going to be like 4 or 5. And we can keep the root page in memory, so that it means for any conceivable application, you can get to any piece of data, even if it's trillions of pieces of data. It's huge file. You can get to any one with only 5 or 6 probes. That's quite amazing. It's really an astounding example of algorithmic technology doing something that you wouldn't really necessarily think that you could do so easily. Maintain a dynamic search symbol table with trillions of keys so that you can get to any key just by looking 5 or 6 places. But that's what B trees provide for us. This is a simulation that shows a growing B tree. So when a page, at the top, there's just one page that fills up. When it fills up, it's red, and that splits into 2 half pages. And then keys get added on one side or the other. So each line in this table, some page is getting a new key, and eventually one of them fills up and splits. Now we have 3 pages, and we keep going. Eventually one of them fills up and splits. Now we have 4 pages, and now this time the first one fills up and splits, and so forth. So the black is the occupied part of the page, the white's the unoccupied part, and full page about to split, then right below there's 2 pages. So this shows the process of building a large B tree. And you can see the amount of black. It's kind of half empty. It's a little more than half empty usually, analysis shows. And people have variants of these algorithms that keep it much more than half empty if that kind of space is a consideration. So as I've mentioned, red-black trees and B trees are widely used as system symbol tables. The Java implementation of tree map and tree set is red-black trees. C++ standard template library uses red-black trees. And it's also used in the Linux kernel and in many other systems. B trees, there's many different variants that give different characteristics of space usage and other characteristics in most databases nowadays that you might use. SQL or Oracle's database and others are based on some variant of B trees because they're so effective. But you really know that your data structure algorithm is used by a lot of people when it appears in the popular culture. My friend Philippe Flageolet, who recently died, but was a famous French mathematician, sent me an email late one night. He was quite excited because he was watching a rerun of an English actually Canadian TV show on French TV. I didn't know he spent his time doing that, but he was very excited because he saw this clip.
It was the red door again,
I thought the red door was the storage container.
but it wasn't red anymore, it was black.
So red turning to black means what?
Budget deficits, red ink, black ink.
It could be from a binary search tree. The red-black tree tracks every simple path from a node to a descendant leaf that has the same number of black nodes.
Does that help you with the ladies?
Not only is there some excitement in that dialogue, but it's also technically correct, which you don't often find with math and popular culture or computer science. A red-black tree tracks every simple path from a node to a descendant leaf with the same number of black nodes. They got that right. And that's also true of B trees, and both of these methods are very effective and widely used.